We start from the first screen. It's a method with changing variable for fitting a nonlinear function to the measurement data of points and its uncertainty band. It's a second part of the developed method with changing variable for fitting of nonlinear function using the least square method. It's the most general method, WTLS. It's a weighted total least square method. It's a generation with all uncertainties for both of coordinates, x and y. Measured coordinates are taken into account, as well as the correlation between coordinates. How it is possible? It is possible that at measurement point, it's easy to find the correlation if you repeated the measurement of both coordinates. But what happened in the next point and the correlation with coordinates with the next? It's possible. It's functionally correlated. Sometimes when I 2 years ago I prepared the presentation about the Venturi nozzle. It's a sonic nozzle. When we try to fit the straight line to the discharge coefficient as a function of inverse of square root of Reynolds number. So we should calculate the both coordinates as a variable from indirect measurement. So it is possible to obtain all possible correlation. In this part, we focus on three selected examples of matching the exponential characteristic of thermistor, matching the parameters of the equivalent capacitor diagram, and determining, as the IMECO in Hamburg this year, the radius of curvature of spherical lenses using the non-contact laser method. Our agenda is a few brief information about WTLS, the possible type of square, depend on the correlation on the value of the uncertainties. Also the estimation of coverage corridor for from the method of Monte Carlo, from the method of LPU, and a simple example for straight line fitting, also the uncertainty band, and the main condition for our method, and also free example as I mentioned before. So let's start. This information is given by Zygmunt, but I only put information about the general procedure for determining the uncertainty corridor, that it's not so easy as for straight line regression. For straight line regression, we have a simple known hyperbolic curve for the limits of uncertainty, but in other nonlinear curve, it's a totally different curve. So we start from the general criteria function. It's the criteria function have the following input parameters like coordinates for x, for y, covariance for x, covariance for y, and semi-covariance matrix like for correlation, and two vectors which is independent variables. It's a vector of parameters and vectors of the coordinate x, because we vector of coordinate xp is a different from vector of coordinate x. It's because we assume that we have uncertainty of every coordinate xe points. It's easy to find that if we have, for example, 10 measurement points and 5 parameters, we have 15 independent variables to minimize such a function. And if we, for example, at the correlation coefficient, the number of input parameters is about 230. And the most recommended method for solving such an equation with, for example, 15 parameters is Levenberg-Marquardt method.
Jacek?
Yes?
We see only first slide.
First slide?
Yes.
Not only next?
Yeah, yes.
It's, but I changed the slides. It's possible. I'm
now production.
Oh, sorry. If I put this slide, you see the first slide.
Now, yes, slide general criterion function.
Yes. Maybe I start from the first from the current slide, and you see the my slide. Okay, I talk about this minimalization of this criterion function. Okay, could you tell me the slide is changed?
Continue.
Yes, type of least square methods.
Yes.
It's an
criterion for function is slide number 4.
And now it's slide number 3. No. Type of least square method. The
square.
Yes. 3.
Previous slide to next.
Yes,
okay.
but I changed the slide. The slide.
You can click number 5 on the left.
You see the slide with the general name type of least square method. Yes. Yeah. Yes, the method can be divided in 3 different simple equation for the criterion function. The first one is when we have the same value of the uncertainty for x and y. We have the total least square method, and when we assume that the error in direction x is 0, then we obtain the OLS method. And for OLS method, we generally we have no knowledge about the variance. So the variance is estimated by the Gauss-Markov theorem as estimator. So in this case, we use estimator. The second is the WTLS without correlation. We have the sum of square normalized error for x and for y.
Ale wpuść piątkę wpuść teraz, tak?
And the final is the more general criterion function when we use all variable with correlation. So you see the Monte Carlo method for coverage for ELSM. You see the slide.
No, to jest czwarty jest ciągle. Musisz pocisnąć
piątkę. Ale Monte Carlo method for coverage corridor now.
Nie.
No.
Jest dwójka. General
Oh,
Chicken.
yeah. So it's not.
Monte Carlo was few minutes.
I talk about this slide. So I must start with the current slide. So I talk about this slide. You see Monte Carlo method?
Yes.
Yes. So it is in mathematics. We have no problem if you have a simple formula analytically with the any mathematical operation. If you have an explicit function, it's easy to find from the distribution, input distribution of any variable in input to find the final distribution. It's only one variable for y, and to very easy for example using quantile error environment estimate the coverage corridor. But the most complicated problem exists when we use Monte Carlo for for fitting nonlinear function, because the parameters can be too much parameters. The function is even is explicit. Is complicated. It's not easy to find the solution for every sample vector of input vector of coordinates, to find the input vector of parameters. And if you want to estimate the coverage region for given x in the given the simple explicit function, first must obtain the all distribution for all parameters. So if you have all distribution, you can easily to find the coverage region for given x. So if you want to obtain all coverage corridor, you can calculate at any point of x. But sometimes it's not easy. The solution of such equation, even is explicit function, is more powerful of computer power, and we need more time. It's and if you add also the correlation in the input, when you obtain, you must obtain the every vector sample with correlated variable. It's more computation time. So the simplest method is to estimate the first derivatives by the numerical differential quote. It's now it's determination of coverage corridor. Yes, you see. So from law of propagation of uncertainty, it is in the linear model. It is easy to multiplicate the sensitivity matrix.
To już jest.
Yes, okay. So the mean value of parameters.
Nie mam pretensji, bo to wie pan, ten komputer do niczego już nie służy. Mnie przynajmniej nie służy. Nie mogę robić tych prac już od paru lat.
Yes, of course. You first calculate the sensitivity coefficient, and next multiply the covariance matrix, multiply by both sides of correlation, correlation coefficient in matrix. Use it So it's a full matrix of correlation.
No
And
może
multiply
pan
both
powolnie
sides by the
normalnie wolny, wie
sensitivity.
pan. No, nie chciałbym się tutaj odrywać z tego komputera. A chyba, że po południu. Ja nie wiem, co dzisiaj.
At the moment you see the following fitting linear regression line for almost the same uncertainty with for X, for Y, and for both. If you take into account both uncertainties, you obtain the highest, the widest uncertainty band. So the solution is almost the same, but the uncertainty, the expanded uncertainty, the standard uncertainty for this model is more complicated. And in the case of you see, no, wait a minute. Oh, okay.
Yes.
In the case of relative uncertainty, the solution of fitting straight line is different, but the best one is when we take into account both uncertainties for X and Y, and then the standard expanded uncertainty is also greater than in other cases. Okay. So the diagram of proposed method, all presented method is based on the following consideration. If you transform all coordinates, one or both, to another variable, you can, with one of even two parameters, θ1 or θ0, you can obtain the straight line to fit to the new measurement points. Why we do such a thing? What for? Because in the case of straight line, it is easy to remove xp vector of variables. So if we, for example, have 15 numbers, the numbers of independent variable will be 5 or 5 minus 1 or 4, because we use the inverse effective covariance matrix. So in the case of straight line fitting, it's possible to minimize locally the objective function, the critical function. So finally, we have only dependent, dependent on θ1. And in the case when we transform y one by one or variable from the oldest one to the new one, then criteria function will be the same. So it's exactly the same solution, but we should know that we must apply the law of propagation of uncertainty. So from one point to another point, we from one variable to another variable, we should multiply all uncertainties at any point by the first derivatives of the transfer function. The main condition for the nonlinear function fitting in our method is divide the all parameters to the theta 1, theta 0. Theta 0 sometimes could be 0 and it's not we didn't then we doesn't list the another parameters and other parameters. So if you have a specific nonlinear function, it's an implicit function, you can divide the data to the x and y, theta 1, and for such a and the new variable can be estimated or can be depend on x, y, theta 1, and beta. Why it is possible? Because during the transformation, the checking equation of measurement, the relation between x and y, we can find the one of the parameters which is linearly dependent on the other. It is maybe inverse function or other. So it always possible to taken one of parameter and obtain such a relation. So maybe I forgot. Oh, it's a relation which satisfy all cases, even implicit function. It's possible to do such a thing.
Jacek, za szczegółowo, bo nie zdążysz.
So let's begin the three example. The first is the equivalent diagram of capacitor. We have 3 resistance and 2 capacitors. The problem is it's not possible to resolve this equation. So find the data from measurement. So the value of resistance and reactance as a capacitors. It's not possible to find the elements of the equivalent diagram. So one of the possible way to fit it's transform the admittance, which is a real and imaginary, in two equation which is can be interpreted in if we put this new variable in the following way. So we have 2 linear equation. So we can apply the effective inverse covariance matrix and find the criterion function. How to do it? Calculate at any point of x of capacitance C1 the criterion function for both equation. Of course, at any putting input parameters which is a part of vector of beta, it is a value which can define the local minimum. It's a semi-parabolic, as Zygmunt shows before. So when we change one of the beta in this case it's only beta 1 and beta 2. It's a resistance RD and resistance R1. We can find the global minimum for both equations. and freely searching beta 1 and beta 2, monitoring the local minimum for C1, we obtain the finally value of the minimum global minimum for objective function, and from this algorithm it is possible to change C1 step by step, and beta 1, beta 2 find the two opposite value for estimated the first partial derivatives. So for every variable RD, R1, R0, C1, C0, it is possible to estimate the uncertainty. Of course, if you find or if you estimate all partial derivatives. It's numerically estimated by different quotas. And the final result is here. It's not far from the ideal because it's very close. Maybe uncertainty or this part is too high because we start with uncertainty 2% for resistance and reactance. And we obtain above 6% for capacitors. So it's a first the fine example. The second one is sorry, because I don't know. It's possible to visible. Oh, yes. So we start with thermistor with such a characteristic, only 2 parameters. It's easy to find, it's easy to fit, but we assume that resistance and also temperature are determined with 2%. Nominal value as here. This is table of all data. It is necessary to tell that we have two T-type and P-type two ports which the thermistor is connected, and finally the characteristic is on the input of the circuits. These two ports are equivalent. It's possible to find the solution. The total resistance is here, and how to find the parameters of the 2 ports. It's depend on the second relatives. Because at this point we start to measure the temperature as a function of temperature, its influence on the resistance, and we find at this point when we have the inflection point, the parameter C, and what we what the fitting of the nonlinear curve. It's only such a simple change of variables, and using the law of propagation uncertainty, it's easy to find both uncertainties in the new coordinates, and finally it's easy to find the semi-parabolic dependence on theta 1 or theta zero, as we know from our consideration that both of parameters are functionally related, and we should find the global minimum. Its global minimum is very close to the nominal values. So as you see, we have such a resistance, and parameters B depend on the energy gap of the material. So it's not so easy to find the coverage corridor. It's very close, but on the next slide we show first the nominal value of the two characteristics for different value of T-type and P-type two ports for nominal value, but it's uncertainty of this line is necessary to find. But first we find the characteristic for correlated and non-correlated variables, and as we see, we have a 0.5% different from the characteristic of thermistor from the non-correlated or correlated measurement. We assume that all matrix Y and X are determined with correlation coefficient 0.2 and correction coefficient for XY matrices -0.2. So when we put it with this characteristic to the formula for two ports, on this, for example, areas depend on the uncertainty of resistance free for T ports, and this port is the uncertainty is determined for this 0.5%. So it's the second. The third. What's the third? It's presented. Oh, sorry. I don't know why it's possible to. Oh, at this point we have a simple measurement of the curved surface. It's possible to measure with spherometer or interference method with Newtonian rings for small curvatures, but in the case when we have liquid lenses, it's necessary to measure the radius of curvature using non-contact method. It's the laser method is the best one, and we reflected the laser beam, the trace on the screen, and we have the nonlinear, of course, equation. If we put both of variables, we obtain the following linear equation, and we try to fit all parameters to the new virtual measurement coordinates. First, of course, you should calculate analytically all first derivatives, and of course the problem is not resolved for H and B least square method, but for the new one. For the new one, it's the value of the criteria function is very close, but as you see at this point, the value of C depends on H and B. We confirm that there was no correlation, but the criteria function is a little different from the beginning consideration, but it's also good condition, because it's condition after simple mathematical derivation. So we use such a effective effective variance, and finally oh, sorry, we have some problem. Once again, the criteria function is we can talk about that is semi-parabolical dependence on R, and we have all the auxiliary parameters, and the final result is here. But what we observe, that the global minimum is cannot be a good value. Why? Because the global minimum for 0.96 is for distance from screen 102.7. It's different from the measurement very precisely in the beginning of measurement. So it's a different value. The value, the correct value is 100. So we must shift the minimum, and the minimum for this case is for criteria function the value 4. So the radius is 50.2 millimeters. From very simple numerical estimation of first derivatives for every measurement, we calculate the total, the standard uncertainty of radius. So at the beginning, we talk about the simple method, very useful, maybe not for 100 parameters of a function, but a few, 5, 4, maybe 7. It depends on the possibility of power consumption and the time to calculate the fitting parameters. One of parameters can be used for obtain the linear relation between new variables. It's always possible. The mathematics give our possibility to use always such a derivation. But during this operation, from the law of propagation uncertainty, we must obtain all uncertainty. It's a approximation. It's an approximation because the new function is maybe more complicated, and so it's not different, easy to to estimate very correctly the uncertainty. But reduce the number of variables. The number of variables may be, for example, in if you use, for example, 60 points to estimate the curve, we have, for example, 60 plus m independent variable. It's not so easy to find the best parameters, the global minimum of criterial function. So the method gives the possibility in a relatively short time to find the fitting parameters if you have